So there was one thing from last time that I wanted to fill in. We ran out of time, slash, I messed up the code at the end of class. So I wanted to kind of revisit that real quick. So this was kind of this dynamic balance thing that we kind of talked about last time, where we had a gyrostat, so a spacecraft with reaction wheels, and we were talking about the difference between like wobble and nutation. So I wanted to kind of dig into that a little bit. So this is the same stuff as we've seen a bunch. The main difference here is that we're going to have an inertia matrix that is not perfectly diagonal. So I'm introducing like a random rotation here and sandwiching this diagonal inertia. So we're getting a more general inertia matrix that's a little off, right? And so the kind of the context here is a lot of times when we're spinning a spacecraft, we want to spin it about some desired like foresight vector or thrust vector for a thruster. And we can never really get the mass distribution just right. So there's always going to be a little this wobble and nutation kind of stuff. And this is kind of how you can fix that. So let's see, here's the dynamic. So what we're going to do real quick is take a look at some of this, right? So the first thing I'm going to do is we'll spin it about this sort of major axis, nominal major axis, right? So Z, but that's not anymore the true symmetry axis, right? So it's gonna have nutation. So let's look at that. So we'll simulate blah blah blah. So I want to go and sample that rotation again and make it a little bit more terrible because it's not wobbling around all that much. Let's see, it's actually extremely clean. Oh, that's because it's. Oh, let's do that again just to make sure. Yeah, that's too close to diagonal. Let's give it a more annoying. That should be a little better. Let's give that a try. So we're going to turn this off. Oh, right. I don't want to do this. Okay. And simulate. Okay, cool. So let's take a look at this. Okay, so this is right. So it's clearly kind of doing some funky stuff, right? And if we look at the angular velocity plot, this is nutation, right? So this is nominal z-axis spin, and then these are the x, y components of the angular velocity. So it's nutating. It's doing the kind of thing we've seen before. So the next thing we can check is I'm going to spin it about now, not the x-axis, but the true inertia eigenvector. So I'm taking the x-axis here, and I'm rotating it by the same rotation that I kind of apply to the inertia matrix up here. So I'm like rotating it into the principal axis frame now. So this is not the x-axis, but it's the correct axis for it to kind of like rotate in an equilibrium spin. So we can do this again. Let's do that, simulate, kind of animate this again. So let's take a look. So right, it's visibly not spinning cleanly about the x-axis, but like if we plot down here, you'll notice what's happening is it's not nutating, right? So there's no wiggling in the angular velocity components. Instead, what's happening is that angular velocity vector is constant. It's just not aligned with the body x-axis because the inertia is not perfectly symmetric. And we can actually calculate by looking at these components over here, this what's called a wobble angle. So this is basically the difference between the true major axis and the body x-axis frame. And you can see here it's about 5 degrees. So this thing's basically coning around about 5 degrees from the body x-axis because of slight misalignment of the mass properties, right? So, okay, so that's cool. So what we can do now is this dynamic balance trick that we talked about last time where we do this little pseudo-inversey thing. And you can go back and look last time at how that works. And we can basically cancel out the sort of off-axis omega cross j omega term using our wheels. And that's what this looks like. So we've got the desired spin. And basically what we're doing is figuring out the row that will cancel out omega cross j omega so that we're making this now an equilibrium. So it's the same exact inertia. And now we're spinning it about the actual x-axis. And we've done this dynamic balance trick so that now I'm spinning perfectly about the z-axis, no component in xy, and no nutation either, right? Cool. Okay. That was just to actually show you the demo from last time that we didn't get to do. Feel free to play with this. I know it's kind of a cool trick. Any questions about this? I don't want to try anything. Okay, cool. That's done. Put that away for next time. And I'll fire up the iPad. Yeah. Okay, iPad. All right. So let's see. Just to kind of figure out where we're at because it's been a minute. Last time we talked about kind of dampings, a cane damper. We talked about gyrostats and basically how to have momentum actuators like reaction wheels in our model. And we talked about these tricks you can play with the angular momentum, internal angular momentum, to kind of stabilize things and get rid of nutation. So this is super spin, which is basically like augmenting the effective inertia about a non-major axis to make it stable using wheel momentum. And then we talked about dynamic balance, which is effectively canceling out nutation about a non-principal axis. So with these two things, we can basically make spacecraft spin about any arbitrary axis we want stably. And I think it's worth pointing out these are not control laws. This is like open loop, right? These are just constants we're putting into the wheel speeds that are kind of reshaping the dynamics in an open loop kind of way, which is kind of a cool thing. Any questions about any of that stuff from last time? Check out the code. Okay, so today we're going to start digging into attitude control. So we've got kind of the first thing we're going to talk about is attitude sensors and like kind of quickly survey kind of the standard options. And then we're going to start talking about static attitude determination. So what I mean by that is basically instantaneous kind of one shot. You get a bunch of observations from star trackers, cameras, whatever sensors, and you're just from that snapshot of measurements at a given time, instant in time, you're going to compute an attitude quaternion or rotation matrix at that instant in time, right? So that's what we call static, as opposed to dynamic, which means you're computing maybe not just the attitude, but also the angular rates. You're using a gyro and a dynamics model potentially to do this kind of in a recursive sort of filter style way in an online setting that's including not just the instantaneous measurement, but some notion of the measurement history and the dynamics in there, right? And to foreshadow, like that's going to be some sort of Kalman filter kind of thing, right? So here's like kind of the instantaneous one-shot version. And then after this, we're going to kind of get into this more continuous in time sort of dynamic version. But for now, we're going to start with the simplest possible case. Okay. Questions about anything? I'm feeling pretty good. All right. So let's sort of, I guess, first of all, like define the problem here. So as attitude estimation is kind of basically um, the core engineering problem is um, how to figure out attitude from onboard sensors. But kind of tied up in this, and I think slightly deeper, is a basic question of uh, how to think about attitude statistically, which is a little bit subtle. So we're normally used to thinking about vectors, right? And maybe Gaussians and stuff like this. And we know how to, average things and take means and maybe covariances and stuff like this. And that all makes sense when you're dealing with scalars or vectors. Attitude, though, is neither a scalar nor a vector, so it's a little weird. So we have to come up with some new notions of, how do we average rotations? How do we average quaternions? What does it mean to have like a mean and a covariance? How do you define a distribution over quaternions or rotations, right? It's all kind of funny and weird. So there's some extra machinery we're going to have to like develop to really do this properly. Uh, okay, cool. So the next sort of thing we're going to do is a really quick survey of attitude sensors. Anyone have any right off the bat thoughts on this? Yeah,
Like star trackers, sun sensors.
star trackers are a good one. Let's write them down. So star trackers are the classic one. So thoughts on how those work, pros, cons, etc. So the gist is you have a camera that images the stars, and then you use one of a few algorithms to basically match up what you're seeing in the camera to a map of the star field or a database of stars. And we're not going to talk too much about the algorithms that do this. They're pretty classical machine vision algorithms. And there are actually a couple of good open source implementations of these if you're into it. So you can actually make your own with like a Raspberry Pi pretty easily with a Raspberry Pi Cam and a couple of the open source star tracker software packages. We're going to kind of assume that you have one of these and that it's spitting out a quaternion, because typically that's how this looks. You buy one of these or you use the open source stuff. So we're going to kind of talk about how to deal with the measurements coming out of them. Let's see some other things about this. So these, unlike some of the other sensors we're going to talk about, they work anywhere, which is good. Issue, let's see, maybe we'll do like green and red for these kinds. So a problem with these things is they suffer from motion blur if you slew fast. So one of the if you try to make these, which I have done before, you find they're really annoying actually in some certain ways. So one of the things that happens with these, so it turns out stars are not very bright. To get good star field images, you need long exposures, and so this is inherently at odds with fast slewing. So if you take long exposure, often the exposure times on these things are like a significant fraction of a second. So if you do any kind of appreciable slewing, you're gonna almost immediately get blurring, motion blur in here. Sometimes there's actually algorithms that can take advantage of that. So they can look at the streaks of the stars and from that infer your angular rate to some degree. So there's algorithms that can use it, but it's usually more of an annoyance than a help.
Well, how do you know where do you start and where do you end if you have like a line?
Yeah, I mean, I think there are some techniques for doing this. It basically amounts to looking at your gyro and doing it in a recursive filter kind of way. You have to know something about the dynamics and and use other sensors. So there are ways of like compensating for this, but it all kind of sucks. And in general, you can't use these when you're slewing more than like 10 degrees per second or so because of these blurring effects. Let's see. So cool thing about these, unlike some of the other options, assuming you buy one of these or whatever, they give you the full attitude. So they just spit out a quaternion. And they have high accuracy. So say order like 1 arc second. Does everyone know what an arc second is? Let's take a degree. You divide it by 60, that's an arc minute. You divide it by 60 again. And that's an arc second. So an arc second is 1/3600th of a degree. It's a weird unit, but they're like kind of standard in pointing applications. The maybe more sane unit would be like microradians, which are sort of close to these, but arc seconds are really common. So I don't know, you'll probably see them. Let's see, arcs. And then, yeah, I would say another sort of possible downside here is if you buy these commercial, they are expensive. Okay, so we have star trackers. You said another one too. What was the other one you said?
Sun sensors?
Sun sensors. These are also good to talk about. So let's see, what do we say about these? So these guys basically measure the bearing vector to the sun. So basically a unit vector. In the body frame. So we'll call this like S with a little B on it. And let's see, some things about these. One negative is they don't work in eclipse. So obviously, if you're on the night side of the Earth, you can't see the sun. They don't do anything for you. Let's see. These are pretty coarse. There's a few ways to implement these, but like kind of the standard. So a way you can do this really cheaply, that's sort of common, is you can actually you can use your solar panels for sun sensing by just looking at if you have body mounted solar panels, for instance, you can look at the solar panel currents on the different faces and get an estimate of the sun vector to within a few degrees. That's pretty common. There are also dedicated sun sensors of various kinds. So there's simple ones where it's a single like photodiode on a face, and you look at that and you take basically the sun vector is related to the cosine of kind of what you see on those guys. So, and then the fanciest ones are little pyramids where they have a bunch of photodiodes on various faces, and these give you the most accuracy. Those can be sort of sub-degree, but I'd say in general, these things are order a degree or two. What else do we say about these? Pro on these guys, though, is they're simple and cheap, and sometimes even free if you just use the solar panels. Okay. Other ideas? Don't have any other thoughts on sensors? That's a good one. Probably gonna start a new page. Okay, so let's see what to say about these. So these measure um, Earth's magnetic field. These are really interesting, it turns out. Irritatingly, the standard letter for magnetic field vector is capital B, which sort of is annoyingly overloaded with our frame. So I don't know. If we deal with these more, I might find a different letter, but we'll go with that for now. Um, so things to say about these. They're actually super interesting. So these are very common for attitude determination in low Earth orbit. They're also increasingly being studied for navigation, like for orbit determination and just generally GPS denied navigation. The reason is that there's like this kind of revolution that's happening around quantum sensors now, where people are able to build like insanely sensitive magnetometers. And if you have a good map of the Earth's magnetic field, you can actually figure out where you are using a magnetometer, which is kind of cool. So it's kind of a emerging thing that's pretty interesting. Let's say so stuff about this. An obvious one is that this is only really useful in low Earth orbit because you need to be close enough. Yeah.
Or is the magnetic field for Earth significantly different at every single point?
It's pretty different. So yeah, like these simple toy models are like, oh, it's a dipole. It turns out it's not at all a dipole. It's only a dipole if you like zoom out and squint. It's actually really wiggly and nasty and complicated. So there's enough richness in it that you can do quite a good job. It turns out, so to do this, you basically what you're doing, it's similar to the Star Tracker thing. You need a map of the magnetic field. And one of the subtleties here is you actually have to know where you are too, right? So for this to work, you have to know what the B vector in the inertial frame is for this to be of any use. And to know that, you have to know both your position and have a good map of the magnetic field of the Earth to sort of look up what it should be and then have like both the inertial frame and then the measured body frame version, right? So these are subtle points, which is, these are all good things. If you don't have orbit knowledge, you can't do this because you don't know what the inertial frame B should be, right, in that location. Um, let's see. So let's write that down too. Only useful in low Earth orbit. Um, let's see. Another sort of, I don't know, maybe bad, maybe neutral, need position knowledge, and magnetic field map, which is that part's not so bad. There are standard maps available that are pretty good. Let's see, other things about this. These are actually super sensitive to electromagnetic interference from electronics on the spacecraft, which is annoying. So basically, any kind of current moving through anything, like current in any kind of wire, generates a magnetic field. And so if you put these inside the spacecraft bus, there's a ton of magnetic noise that they're very sensitive to, which is very annoying. So spacecraft that are trying to do really accurate magnetic field measurements actually will put the magnetometer out on a boom away from the bus electronics. The other sort of interesting thing is that magnetic field strength falls off like R cubed. So it falls off really fast as a function of distance from the source. So you don't have to get that far away for the interference to taper off very quickly. So an approach is to stick it on a boom out a couple meters from the bus. Let's see. Let's write that down. Issues with interference. The other kicker is that often on low-cost spacecraft where you'd like to use magnetometers, you also like to use magnetorquers as actuators, and obviously those saturate the sensor and so you blind you. So there's very annoying issues with this. What else? These are pretty coarse, similar to the sun sensor, kind of few degrees. And that's because both because of the mapping and the need to know where you are kind of piece and having maybe not a super accurate map, and because of the interference issues. So it's always kind of limited to, I would say, a few degrees. You need calibration to get it better, but they're always kind of crappy. And then the last one on the pro side, these are very simple and cheap also. So classically, I would say on like CubeSats and small low-cost spacecraft, sun sensor magnetometer is a classic combo because they're like almost free. Okay, other ideas. What else we got? Someone, yeah, you were kind of sorry.
Earth horizon sensors.
Earth horizon sensor. Yeah, so there's a whole bunch of things to say about this. I guess we might call these Earth sensors. So the gist is these guys measure angles to the horizon. And that's kind of in all directions, right? So you imagine looking out from your spacecraft, the horizon goes out, 360 all around you. So from this, if you kind of measure the horizon this way and the horizon this way, you're getting two angles. And effectively, the output of this thing is a nadir vector. As you imagine, have these two angles, which you're really getting out of that in the end is like the unit vector pointing down towards the center of the Earth, right? And then again in the body frame. Okay, so let's see. Things about this. These only work in low Earth orbit, once again, because you're depending on the Earth. These are sort of moderate accuracy. So these are, say, you can, if well calibrated, etc., these can get down to like 1/10 of a degree. So pretty good. And they're also relatively simple and cheap. Okay, other ones.
So, scopes and accelerometers.
Yeah, so gyro, yes, absolutely. Accelerometer, not so much. If you're in orbit, you can have a non-zero measurement on an accelerometer just because of like an omega cross R term if you're spinning and it's off the spin axis somewhere. But otherwise, if you're just hanging out in orbit, accelerometers measure zero, like by definition, because you're in free fall. So those are less common. But yeah, definitely gyros. So these guys, we've already talked about these, right? And it's sort of obvious. These measure your angular rates. So they literally give you omega in the body frame, almost like idealized, right? Um, what they really give you is a noisy version of that with a time varying bias. So they always have a bias, as in if you sit it still on a table, it doesn't measure zero. So you have to kind of subtract that off and figure out what that is. And then they also have additive noise. And the bias is time varying. It drifts over time, which is annoying. So we'll get into this when we talk about Kalman filters. You basically always have to estimate out the bias vector on these guys and do some other filtering ththings to make them work in practice. And there's also a huge variety on these, ranging from like $2 chip MEMS ones that are in your phone that we use on small sats to like $20,000 fiber optic like laser gyros that are high end and used in expensive aerospace platforms. Um, so huge variation in cost and performance. What else is there to say about this? There's also some fun things. There's some open source projects online where people have made boards with like 40 cheap gyros and filter them together to get the angular random walk, like the noise down, which is kind of cool. Kind of into that. Okay, let's see. What did we not get to? Any other thoughts? There's a couple other ones. Anyone have any other ideas?
Terrain relative to that.
I would say this isn't so much. So we've done some stuff like this as a research thing, but it's not so much used for attitude determination because there's typically easier ways to get at attitude. And doing that's it's a gnarly machine vision problem. It's been used obviously for power descent guidance, but it's more for figuring out where you are location wise and less for just attitude. Though we've done some researchy stuff where we've used it for joint attitude and position determination, which is hard and kind of dumb, frankly. It gets a lot easier if you just throw a star tracker on there. Other thoughts? Any other ideas? It's a couple other ones. Okay, so another one that is interesting is GPS actually, which is maybe less well known. So, did anyone have any idea how you do this with GPS? It's kind of fun. Yeah.
You need like multiple receivers.
Yeah. So everyone heard of like RTK or carrier differential GPS? So it turns out with GPS, right, your absolute position knowledge for a GPS antenna is maybe like 10, 20 meters, something like this. But if you have two antennas that can directly compare the phase of the GPS signal, they can get their relative positions super precisely, like millimeter level relative positions, right? So that trick, you can play that trick with multiple antennas on a spacecraft. So if you have, say, three antennas that are spaced, I don't know, a meter apart on the spacecraft bus, you can measure the relative positions of those three antennas super, super precisely, which effectively gives you three baseline vectors where you know them in the body frame because you literally stuck the antennas on the spacecraft, and then you know them in the inertial frame from the GPS receiver. So this can get you pretty decent attitude determination. This has been used on orbit. So let's try to draw this. So you need three or more antennas, and you do what's sometimes called carrier differential GPS, also known commercially as RTK, is what they call it for surveying. But you can like buy these things on SparkFun now. They're extremely accessible. And what these are kind of getting you is what we'll call baseline vectors. So the cartoon is I have my little spacecraft bus, and then I've got, say, that's the wrong way. That is the circuit symbol for antenna, those who didn't know. So you got these guys, and then you have sort of, kind of the vectors between these, right, in the body frame. And then by measuring this with the receiver, you get it in the inertial frame. So this gives you three vectors that you know both in body and inertial frame, and then you can figure out what's going on in terms of attitude. And these have sort of moderate accuracy, we'll say. kind of that 0.1 degree level. Okay, did I forget anything? I think that's about it. It's a decent survey. Any other things people would think about? I think that's pretty good. I can't think of anything else. Yeah.
Does like Doppler radar measurements count as attitude determination?
Um, so yeah, you can absolutely infer things. So for instance, like a problem classically with comms, with RF comms, is fading due to satellite angular motion, right? Like the antenna is kind of going in and out of view. And you definitely would get like periodic Doppler stuff from this. I don't know of anyone using that for attitude determination, but it's certainly possible. You could do something analogous to this GPS example if you had like another known signal source and you had multiple antennas on the spacecraft that were listening to that signal and then comparing phase. You could get kind of relative phase information that you could turn into angular information. So you could do something like this. Um, it's the same general idea as the GPS thing, I would say, but doing it with other signal sources would be tricky. You'd need to know them. You need to know where the signals were coming from really well, and it would take multiple signals, right? Because you need multiple kind of baseline vectors and direction vectors to do it, and they'd have to have enough bandwidth to sort of resolve the angular difference enough, right? So like UHF signals probably wouldn't be good enough. You'd need something with wavelengths, tiny enough to measure enough of a difference. And then you'd have that like integer ambiguity problem also. So you need to modulate it with something. You could do this, but I don't know of anyone doing this. And it seems slightly tricky. But I don't know. You could do something like this if you cared. There was a good reason to. It's kind of interesting thing to think about. All right, cool. Anything else on this? I think we're good. All right, let's get into it. So that's how you sense. What we're going to talk about now is sort of the granddaddy of all attitude determination algorithms, which is called TRAID. Has anyone heard of this before or tried it before? Nobody. Okay, cool. That's good. We're all learning something. So this is the first ever attitude determination method. And it dates back to the early 60s. And it was developed for and then used on the US Navy transit spacecraft. Has anyone heard of this transit program? Super interesting. Again, like space nerd kind of rant. We talked about all the early spy satellite stuff kind of before. This is also a super fascinating like early space history thing. Transit was the first ever navigation satellite system. Predates GPS by like 30 years. The story here is really fascinating. I highly recommend going. There's like a couple of like history of transit things floating around online, and there was some 50th anniversary of transit like retrospective thing. What happened? There were two guys who were fresh out of grad school working at the U.S. Naval Observatory when Sputnik launched, and they were amateur radio ham enthusiasts, and they like using like their ham radio gear listened to the signals from Sputnik and noticed that it had a significant Doppler shift that you could obviously hear in the audio as it flew overhead, right? So everyone knows Doppler shift, right? As it comes at you, the frequency shifted up, and then as it crosses over directly overhead, it's zero shift, and then as it moves away from you, the frequency shifted down, right? Like the train going by you situation. So they had the idea of, hey, that's interesting. I wonder if we can back out the orbit from the Doppler curve. And they spent the weekend borrowing time on the mainframe computer at the Naval Observatory, coded up a nonlinear least squares solver, and backed out the orbit of Sputnik from a couple of these Doppler curves that they got from their ham radio stuff. And it turns out their OD numbers were some of the best. There were like all these professional astronomers trying to do this and militaries, whatever, everyone was into this. They got some of the best, most accurate sort of orbit OD numbers for Sputnik from this kind of weekend hobby project. Then they went and talked to their manager on Monday about it. And then he kind of raised the question of, well, what if we turn this around? Can you broadcast from the satellite and then listen on the ship and figure out where the ship is? And that's how transit was born. And they literally built this within a couple of years after that. Super impressive. Like this was the earliest days of satellite. So they were like figuring it all out as they went. And one of the things they had to figure out was attitude determination. It's a cool story. And like highly recommend going and Googling this. I'll post it on Piazza later too, I guess, if anyone's into it. And this kind of spawned satellite navigation. Okay, so sidebar. But so the gist here is, okay, question for the audience. How many vectors do I need to uniquely, so when I say vectors, I mean measurements, right? From these sensors, right? So most of these sensors give you some sort of bearing vector, right? They're giving you like a unit vector to something. It's the sun, the magnetic field, the nadir vector pointing down at the Earth, vector to a star, right? So how many of those vectors do I need to figure out my attitude? What do we think? Is one enough? Why not? Why isn't one enough?
Isn't there ambiguity about?
That's exactly right. Yeah. So if I have one bearing vector, I could arbitrarily rotate around that vector. So that constrains the attitude in like 2 DOF, but it doesn't constrain the third degree of freedom. So I need at least two linearly independent vectors to uniquely determine an attitude. Cool. So two is the minimum number. And triad basically takes that minimum two and does some linear algebra to back out the rotation matrix. And yeah, linearly dependent, obviously, because if they're parallel, this doesn't help. So they have to not be parallel, sort of obviously. Okay, so here's kind of the recipe. We'll assume two unit vectors. And the gist of how this works, you need to know them both in the inertial frame and in the body frame. So knowing them in the inertial frame is you have some kind of map or something, right? So i.e., like, I don't know, I know the sun vector by knowing the date and the Earth's orbit and stuff like that, or I know the magnetic field vector inertially from knowing my orbital position and having a map of the magnetic field. I know the unit vector to that star because I have a star field map, whatever it is, right? So you need a map of some sort to have kind of this baseline knowledge of what the thing should be in the inertial frame. Uh, and then your sensor measures it in the body frame, right? Okay, so we're going to write this down as, so we'll call these vectors R. So we'll have R1 in the inertial frame and then R2 in the inertial frame. And then we've got our rotation matrix here, rotates from body to inertial by our eternal convention. And we've got R1 in the body frame, R2 in the body frame over here, right? So we've got these 3x2 matrices basically, and they're related by the rotation matrix. So the gist here is what we'd ideally like to do is, like, roughly speaking, take this guy, multiply by its inverse over here, and that should be the Q, right? We can't quite do that because it's not, it to be invertible, it's got to be 3x3, right? So the trick here is we need to invent a third column somehow that's linearly independent from the first two so that it's invertible so that I can go do that. Anyone have any ideas? How do I invent a third column that's linearly independent of the first two? Linear algebra. Exactly, yeah. So for those who've taken linear algebra before, apologies if you have not. Yeah, if I've got two linearly independent vectors, easiest thing I can do is I can take their cross product, and that'll give me a third vector that is linearly independent of these two. So super, super easy. So now we've got R1, R2, R1 cross R2 in the N frame. And then we've got a rotation matrix here. And we've got R1, R2, R1 cross R2 in the B frame. So we'll call these matrices now capital R in the N frame, capital R in the B frame. Cool. And so, yeah, like we said, it's super easy. I said linearly independent a bunch of times, and that is important because I need the columns to be linearly independent for the matrices to be full rank and invertible, right? So if, and that's like physically just the fact that these vectors, if they're lined up, I can't constrain that last degree of freedom, right? So corollary to this, they need to be pretty linearly independent. So from a physics perspective, if they start to get close to each other, that's bad, right? Because there's always noise. So if they're close to each other and there's noise, my ability to figure out my attitude is bad. How that manifests in the matrix is the matrix is going to become almost singular and you'll get a bad answer. Almost singular, I'm now going to like tell you lots of linear algebra things because I think it's useful. Almost singular here, the way numerically we talk about this in a computer is ill-conditioned. It has a very, very large condition number. Has anyone heard of condition number? So if it has a big condition number, it means it's almost singular. It means it's not almost not invertible. And from a floating point computer math perspective, if a matrix has a big condition number, that means when you do stuff with it, you'll get a ton of floating point error, like round off error, truncation error. So your answer will be crap, basically. The rough order of magnitude thing here is for every like order of magnitude of your condition number. So if your condition number is like 10 to the sixth, for instance, you'll lose 6 digits of precision in your answer. So there's kind of this soft, like invertible or singular versus, not invertible, non-singular, whatever. It's not really a hard thing. As soon as you go into a computer and floating point math, because there's finite precision and round off and all this stuff, it's really a continuum thing. And the measure of how close you are is this condition number, which is conned in MATLAB, Python, Julia, blah, blah, blah. So that's kind of how you could check this. And you should know if you're ever doing this stuff in real life, check the condition number on your matrix. Because if it's really big, i.e. if it's like starts to be like 10 to the 8th, 10 to the 10th, your answer is going to be garbage. So that's, I don't know, fun facts, things I think you should know about in life that maybe you haven't heard about before. This is like street fighting math skills, as Stephen Boyd would say. All right, so that was a long. As long as R1 and R2 are linearly independent, then these big R matrices are invertible. And now we've got Q from B to N is Rn RB inverse. Pretty easy. Okay. Not so bad. So this is like how I would do this now. But in the 60s, when they had really crappy onboard computers, inverting a 3x3 matrix seemed like a lot. So they came up with clever tricks to avoid the matrix inverse. So I'm going to tell you about those tricks now because they're kind of fun and they're historically interesting. And this is the classic triad method. So there's a trick to avoid the matrix inverse. So we're going to define a slightly tweaked version of those R matrices now called capital T, which is T for triad from the original method. And what we're going to do is we're going to build this T matrix so that has the same information as the R matrix, but we're going to build it such that it's orthogonal from scratch. And then if it's orthogonal, its inverse is its transpose. So now I can do this much more easily and I don't have to compute an inverse. That's the game. So to make it orthogonal from the outset, what we're going to do is we'll start with R1, but then instead of just using R2, I want it to be something that's orthogonal to R1. So we're going to use our friend, the cross product again. And we're going to just take a bunch of cross products, so everything's mutually orthogonal. So what we're going to do now is instead of just using R2, we'll take R1 cross R2 and then normalize it. And we'll start calling these guys. So we'll call the first one T1, and the second one now we'll call T2. And I guess we'll put a line in here. And then again, the same thing. So now we'll cross T1 and T2 and normalize it to get the last column. And now we'll call this T3. And then, yeah, so that's the TN, that's the end frame version. So I guess these are all in the end frame. And then we'll do the same thing for the B frame in TB. So I will skip that. Same as the other one, but it's the body frame ones, right? Everyone cool with that? So now I have same as before in terms of these T matrices. So I've got T end frame is Q B to N T B frame, right? So it looks exactly the same as the R version, but now because T is orthogonal, I can just do a transpose instead of an inverse. And this is the classic triad algorithm. So classic triad algorithm, you get your two vectors, you build these T matrices by taking a bunch of cross products and normalizing, and then you back out the rotation matrix like that. Simple enough. Cool. These are things people had to think about hard in the 60s when they did not have backslash. All right. So let's see. What do we say about this? It's really simple to implement. It's about as easy as it gets. And this is still used on like cheap small sats and safe modes and things like this. But it has a bunch of limitations. So the first is that it can only handle two observations. Which obviously limits you in terms of accuracy, et cetera. And like kind of the gist of this is there was no statistics in here either. There's no notion of noise, how good are these measurements, because this is the bare minimum. So you just get what you get. And to kind of do better than this and incorporate more measurements, we're going to have to start thinking about statistics and averaging, basically, and how to combine these things. So let's say no uncertainty or sort of covariance information. And then the last one is this is static. So it's a one-shot thing. It only gives you, instantaneous attitude given instantaneous measurements. It has no notion of kind of averaging stuff over time, incorporating, some model of the motion or a gyro or anything like that. No dynamics. Okay. That said, it's a classic. You should know about it. And I guess we'll do a quick demo. Oh, that's annoying. Yeah, let's take a quick look, see if this works. Yes, it works. Great. Okay, so we're going to make a random attitude. And like we've been talking about in here a bunch, the nicest way to do that is to sample a random vector from a Gaussian and then take the hat and then exponentiate it. And that always gives you a valid rotation matrix. Hint, hint, when we start talking about statistics of rotations and how to think about means and covariances and things like this is basically what we're going to do. We're going to use the exponential map so that we can just think about Gaussians on vectors, and then we map it over to rotations through the exponential. Foreshadowing. Okay, so that's a random rotation matrix now. We're going to make some random vectors, and we'll make them in the body frame and normalize them, and then we'll create the inertial frame versions of them by rotating them by our rotation matrix, right? So this is just making up the data. Oh, what did I do? Oh, yeah, that's dumb. What did I do now? Oh, yeah, got it. Okay, so we got our data. Now we're going to make the R matrices like we just did, R1, R2, and then we cross them. And now we'll use, I guess, backslash, we'll use an inverse to do that. We'll check stuff. They match to machine precision. And then we'll do it the triad way. So we do cross product, normalize, blah, 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 to make T matrices. And then here we can do it with a transpose instead of an inverse. And yeah, answer to machine precision. They match. Cool. No surprises. It's not super interesting. Let's do some more stuff. Hooray. All right. Any thoughts or questions on that? Fine. It's happening. Okay. So how are we doing on time? We got some time. All right. So here's what we're going to do now. So this is kind of the most basic thing you can talk about. So we're going to now start talking about kind of statistics and estimation and all that good stuff, and basically how to do least squares for attitude. Who's done least squares before? Please say everyone has done least squares before. Yes, good. So basically, that's all good, and that works for vectors, right? So now we got to talk about how do you generalize that or think about that for attitude or for rotations. And the answer is something called Wahba's problem. This is a fun little historical anecdote. The Wahba here is Grace Wahba, who is a statistician. And this Wahba's problem was posed as a challenge in like a journal in, I think, 1964. It was like kind of put out as a challenge to the community. And then a bunch of people published their solutions in like the next issue of the journal. And turns out there were like, I think, 4 or 5 different versions of the solution that were published. And the one that stuck is one that is based on an SVD that we're going to talk about maybe today or maybe tomorrow. But yeah, Grace Wahba was a statistician who like was not involved in space at all. And this is like a weird random footnote on her career. That is what she's most famous for now, which is kind of funny. Okay, so question is, how do we kind of average more than 2 observations? And what we're kind of ultimately going to do is least squares. So here's kind of what this looks like. So we define this least squares cost for attitude. So this is sometimes called the Wahba loss function, and we're going to call it C. To be clear, it's a function of a rotation matrix Q, and it's a sum over all our observations K. And to be a little more general, we're going to stick this W on the front here, which is a weight. And I'll talk about that more in a sec. And then inside here, so we've got our inertial frame vector minus Q times our body frame vector. So the idea here is if there's no noise and everything is perfect, Q times this should equal this, right? And this should be 0. So Q times the body one should equal the inertial one. So if there's no noise and you know the attitude perfectly, this should all be 0, and then you sum up the errors and it's all 0, right? If there's noise and inconsistency in the data, then you'll have some residual error in here. And the problem is going to be to try to minimize the sum of the squares of the errors, right? So this is, I don't know, how you write down a least squares problem for attitude. And to be clear, right, the R's are the data that you're given, and the Q is the thing you're solving for. So it's a little weird. What else to say about that? Yeah. So let's see, these are scalar weights. And the idea there is if you have data from different sensors that's of varying quality, you want to trust some sensors more than others. So you'll upweight the trustworthy ones and downweight the noisier, crappier ones. And to sort of put that in more formal lingo, the weights should be inversely proportional to sensor noise. So specifically sensor noise variance. And if you do that, then and solve this problem, you'll get what's called a maximum likelihood solution by like properly weighting things according to how noisy they are. Okay, so let's see. The game is we want to solve the following optimization problem. We want to minimize that Wahba loss function up there over Q. And then we have a constraint that Q has to be a valid rotation matrix. So this is fancy math notation. Q is an element, that's this weird little squiggly E thing of the SO3 group. So another way of writing that is equivalently as we've seen, right? This is equivalent to Q transpose Q equals I and determinant Q equals 1, right? So this is just shorthand for this. Okay. Yeah.
For the subscript for W and
W, so they're supposed to all be Ks. Apologies if my handwriting is terrible.
okay, they look like
Yeah, so it's Ks, yeah, sorry. K. I'm basically always going to use Ks for subscripts. Try to be consistent at least on that. So it's measurement K, right? So each measurement, you've got the inertial frame version, which you're looking up in your map. You have the body frame version that you're getting from your sensor, and then you have a weight attached to it. So those are all indexed by K. And you're going to sum up all the, yeah, you get the idea. I know it's just, sorry, handwriting not great. Okay, so any questions about this? Has anyone seen this before? Nobody's seen this before. Okay, cool. That's good. So yeah, this is the famous Wahba's problem. And let's see, shows up in a lot of different contexts, actually, not just spacecraft stuff. Many solution techniques. So there's a bunch of ways to solve this, and we're going to talk about 4 specifically for various reasons. And the reason is that this is like as posed, it's a weird problem. And as originally formulated here, it's a nonlinear problem. It's like nonlinear, non-convex, blah, blah, blah. So there's not, at face value, it's not an easy problem. But it turns out there's enough like special structure in this that it is actually solvable, sort of almost in closed form. But you need some tricks to get there. So, and each of the methods has, I would say, like, I don't know, broader lessons to be learned. Like each has its own little, nugget of insight that I think is worth talking about. So we're going to talk about the first one, which is the closest to just straight up solving that optimization problem, is a convex relaxation. The second one is an SVD method, which is the closest to the original published solution from the mid 60s. Though back then they didn't call it an SVD because they didn't have nice numerical linear algebra libraries that had these things. but it was essentially an SVD. The third one is one that's maybe the most widely deployed in actual like practice on spacecraft, which is called the Q method or the Davenport Q method, which is a reformulation of this problem in terms of quaternions instead of rotation matrices. And then the last one, which we will, which I think is the cleanest bridge to Kalman filter land, which is kind of the next topic after this, is to use Newton's method to solve this thing kind of directly. That's for next time. But who in here has done Newton's method before? Coded it up, played with it. I know you have. Has anyone not done Newton's method before? Why do I not trust you? So like, yeah, so I might then spend some time on like what that is and how that works for the uninitiated. Okay, so that's what we're gonna do, kind of in that order. So we'll start then, we got time. So we're gonna kick it off with this convex relaxation story, which is a fun story. And this is actually, funny enough, the most recent of the methods for various historical reasons. And I actually figured this out as a grad student, I think before it was published by anyone. And I didn't know at the time because I was dumb that I should publish it. All right, so we'll take a closer look at that Wahba sort of cost function. And basically we're gonna like FOIL it and do some simplifying that is kind of interesting, I think somewhat insightful. So we got this function C and sum over K, not N. And we got these weights, and then it's the 2 norm squared of this thing. So I'm going to expand that out and write it as a squared thing. So we've got the R's in the N frame minus Q times the R's in the B frame. And then, times itself, right? Squared. So that's sort of step one. I'm taking, 2 norm squared, and I'm actually just writing the thing out squared times itself, right? So far, so good. All right, so the next move is I'm going to FOIL that thing and expand it out, and we'll look at the individual terms. So we then get, so first we get R times itself. Then we're going to get the cross terms in the middle, and I'm going to group those together and write that as 2Rn transpose QRB. And then we get the last term that looks like RB transpose Q transpose QRB. Okay, now let's take a closer look at this. What's the first term? What are the R's? So that's Rn times itself, like taking the dot product with itself. What's Rn? It's a unit vector, right? Some unit. So what is that first term then? It's a unit vector dotted with itself. It's 1. So that first term is a constant. It's always 1, so it drops out. Okay. How about the last term? What's that last term? Yeah, y. So that's also 1 and a constant. And the reason is, so Q transpose Q is identity. And then, so that drops. And then this is RB times RB then. So that's, again, unit vector dotted into itself. So that's also 1. So this whole term drops out as well. So this weird least squares thing just simplified down a whole lot. And what we're ending up with now is just this stuff. Minus 2, then it's the N frame 1 transpose times Q times the B frame 1. Okay. So one sort of initial message here is we start out with a least squares function, which is quadratic, right? It's a quadratic thing in Q. But we did this like FOIL business, cancel a bunch of stuff out because it was constant. And then we get down to this thing. What kind of function is that of Q? It's not quadratic anymore. It's linear. So it turns out, weirdly, which is very unusual and very different from standard least squares problems. Normally, least squares problems, squares, it's quadratic. Here, though, because this matrix is orthogonal, so this quadratic term cancels out as a constant. So now we end up actually, it turns out the least squares objective here, it turns out is linear and not quadratic, which is a weird, sort of unusual thing. Okay, now we have to take a little side detour. So I'm gonna try to like teach you linear algebra now as a general thing because I think it's important. Um, I'm gonna teach you something called, I just call it the trace trick. It maybe has a fancier name. I don't know. It shows up often enough. Ever know what a trace is? A matrix. So it's I sum up the diagonal, right? So traces are fun. They do interesting things. In particular, um, if I have something that looks like X transpose A Y, actually, I don't know. Let's do this first. It turns out, okay, so this is a scalar, right? So I can just wrap that in a trace and it doesn't do anything. That's a legal move. It turns out then inside a trace, I can arbitrarily permute the stuff inside and it doesn't change the answer. So I can basically cyclically permute these entries. So that means this is equal to trace YX transpose A. It's also equal to trace A YX transpose. So a bigger picture message here, which I think is maybe clearest, is trace gives you a way of mapping between inner products and outer products. So if I have like the dot product between X and Y, so X transpose Y, versus I have the outer product XY transpose, which is a big matrix. So the trace of the outer product is equal to the inner product. That's sort of, I think, the overall message of like what's going on here. It lets you kind of go back and forth between inner and outer products, and that's sometimes useful. So maybe think about that for a second, write it out or something in components to get the gist. Okay, so this trace trick thing shows up actually somewhat often. So just file that in your brain, and we're going to use it right now. So we're going to take the last step of this Wahba thing, and we're going to play the trace trick. So we're going to go wrap it in a trace. I guess we'll pull the minus sign out and the 2 out because those don't really matter. And then we've got trace. And what I'm going to do is I'm going to wrap that in a trace, and then I'm going to permute it. So I'm pulling the Q out to the right. That's the goal. So what I get from that is I'll get the sum with the weights, and then RB and RN transpose. So I basically took the RB and moved it over to the left, right, to be the first entry. And that's all the stuff that has indices on it. So all the sum stuff is in that grouping, in that parentheses. And then I've got the Q over here now. Okay. The reason we did this is this thing in parentheses with the sum on it is a useful thing that shows up a lot. So it has a name. This we're going to call B, and it's called the attitude profile matrix. And then also from this, it should be obvious now that we've kind of like isolated things and pulled the Q out, that this thing is linear in Q. So it's just something times Q, right? Which is weird because we started out with a least squares E quadratic thing. Okay, so now having played these games, we can rewrite Wahba's problem. Like so. So we have this minus sign. That's important. And then we have the 2, which is not important. We're going to throw the 2 out. So what I'm going to do, because of the minus sign, I'm going to switch from minimizing to maximizing. So I'm basically, minimizing a negative thing is the same as maximizing the positive thing, right? So we'll do that. So now we've got max over Q, and this thing simplifies down super nicely. So we've got trace B, which, remember that attitude profile thing, that's a constant. That's the data, right? So I basically compute this B by summing up over the data, and it's just a matrix at that point. So it's B times Q, and then subject to my SO3 constraint. So we need Q transpose Q to equal the identity, and we need determinant of Q to equal 1. Okay, so this is exactly the Wahba problem, just rewritten a little bit using the trace trick and kind of defining this attitude profile thing. This is like cleaned up pretty nicely now and looks like fairly simple. Couple notes. So this thing is linear. The objective function here is linear in Q, which is nice and simple and generally a good thing. But these constraints are nonlinear and annoying. So we need to sort of think about that a little bit. So nonlinear and what I would call also, which might not make sense to you at this point, but we'll talk about it, non-convex. Has anyone heard of this before? Like thought about convex? Oh, okay, yeah, we'll talk about it. In fact, we'll talk about it right now. Okay, so we got like 10 minutes. Let's see. This is a deep topic. There are whole classes on this. I'm going to give you the 5-minute version, but I'll also post some stuff for like your reading pleasure later. So we need to talk about like what's going on with this optimization problem, what's going on with optimization problems in general. There's basically there are easy optimization problems that you can always get the answer to, and then there's hard optimization problems, which is most of them. A particular kind of optimization problem that is easy is called a convex optimization problem. So I'm going to explain a couple things right now to tell you what that means so you kind of understand it, and then yeah, we'll go from there. So the quick and dirty introduction to convex optimization. So the first thing we gotta know about is a convex set. Who's heard of this before? A couple people. You want to give me a quick definition?
Yeah. Basically, yeah, you can draw like a line segment between any two points.
Bam, you got it. Okay, so here's what a convex set is. I'll draw you a convex set. So this is a convex set. So the definition is, if I have a convex set, I can pick any 2 points in the set and draw a line between them. And the line has to be completely contained in the set. So this is a convex set. I'll draw another set, the banana. And so this, for example, I can pick 2 points like over here and draw a line, and that line leaves the set, right? So this is not a convex set. Okay, so pick any 2 points in the set, draw a line between them. If it's always inside the set, it's convex. Good enough? I got that. So yeah, things that are convex are boxes, spheres, cylinders, ellipsoids, right? Like, I don't know, intuitively, these are examples. So that's convex set. And then the next thing we need is a convex function. And there's many, many equivalent definitions of convex function. I will give you the simplest geometric one based on like bootstrapping on our definition of convex set. So a convex function is a function. Let me draw a cartoon of one. So I'm going to draw like a nice little like quadratic bowl, like parabola, right? And then I'm going to draw what's called the epigraph of the function. Has anyone heard that word? Epigraph? What's epigraph?
Thing, like underneath 2 lines or two points on the
So it's the basically the area above the function. So this is so if this thing we got a quadratic bowl, the epigraph is this area above it. It's everything above the curve. So this is called epigraph. And I guess, yeah, this is x, this is f of x. Okay, so a convex function is a function whose epigraph is a convex set. So the like classic prototypical example is a quadratic bowl. Like that's kind of the standard example. Quadratic functions are convex. Linear functions are also convex, right? Line, everything above the line. Cool. Okay, so that's the definitions we need. And then from there, we can define a convex optimization problem. Okay, so convex optimization problem looks like so. So we're minimizing a convex function f of x subject to convex constraints. We'll write that as c of x less than or equal to 0. You can write it a bunch of ways. So this is a convex function. And this is a bunch of constraints written as some kind of inequality, that defines a convex set. So we're trying to minimize a convex function over a convex set. Why do we care about this? Do you have any insight? Why do we care?
Really easy to solve your big algorithms.
Yeah, so that is why we care. The kind of slightly expanding on that, convex optimization problems like this, you can always find the global optimum, like certifiably, in polynomial time, which means fast, basically. Or you can actually certify it's infeasible. So if you give me a convex optimization problem, I can either hand you the answer, the global minimum, or I can hand you a certificate saying, hey, this problem doesn't have a solution. This is an infeasible problem. You gave me a bad problem. So I can not only solve it reliably, I can also tell you that it is impossible to solve. So you can basically know everything there is to know about it reasonably quickly. Um, cool, quickly. So this is like the gold standard, and this shows up a lot in control. Like, so every kind of like aerospace control problem, like the game is to try to get it into some convex optimization problem form. So like the rocket soft landing problem is like the most famous example of the last decade or two of this, where they figured out some magical tricks to turn the control problem into a convex optimization problem so that it can be solved with guarantees online on the rocket, right? So this is how like we land on Mars and SpaceX lands rockets and all that good stuff. Good to know about. Okay, so that's that. And then some examples of classic sort of standard forms of these guys. That you may or may not have heard of. The first and sort of simplest is called an LP or linear program. And not surprisingly, that means f of x is linear and c of x is linear. The next one that shows up all the time in control land are QPs, which is short for quadratic program. And this is where f of x is quadratic and c of x is still linear. There's like a hierarchy of these, by the way, right? So every LP is a QP, just because, yeah. And then the next one up the chain that shows up quite a bit as well, actually shows up in the rocket soft landing problem, is called an SOCP, which is short for second order cone program. By the way, program is an old school word for optimization. That's why they all say program. And here, f of x is linear again. Can be quadratic also, but the solvers are typically assume it's linear. And then c of x is a cone. And by cone, I mean like standard ice cream cone, the cone you imagine, which is also obviously a convex set, right? And then the most sort of general of these that has a standard solver, which is actually what we're going to end up needing for this, is called a semi-definite program. Or SDP. And these also show up a whole bunch in like classic, like robust control kind of settings, like for designing linear control laws. Here, f of x is linear again. But now c of x is positive semi-definiteness constraint on a matrix. So it's saying a matrix has to be positive semi-definite or positive definite. Okay, we're out of time. So I'm going to break there. We'll pick it up here next time.